So, thanks for standing on this Friday afternoon, Friday morning. So, as Noémie said, I will give you a general notion on AI machine learning applied for corrosion. I would say I have a two-hat role because I'm still doing research with Belgian universities, and I'm also the founder of a AI consultancy company. But today I will show you the highlights of my scientific outputs so far on this topic, of course. And please feel free to interrupt it at any moment. I don't want it to be super heavy, so if you find some difficulty understand some part, please let discuss. Although otherwise, of course, we will still have the time for discussion. I think the reason why we are all here today is because there's nothing we can do anymore, in my opinion, to stop AI. Corrosion is everywhere nowadays, as well as AI. So we shall better discuss and understand how to implement and use this technology the best way possible, right? And in my opinion, the only best strategy is through education and learning. In terms of material science, specifically, even before 23, even before the launching of GPT, there was already very hype on the use of AI in material science. I have no definitive answer to why, but from research, I realized that material scientists were the one with the highest adoption rate of AI technologies until 21, 22. And as already mentioned, you all know that at the end of 22, and especially during 23, we have this huge hype of AI due to the launching of ChatGPT by OpenAI. And what really changed was that AI left academia, and where it was used as a discriminative tool, and also in big companies as well, and it became a generative power. The genius idea behind it was to put the user in the center of the loop. The user can easily use AI and get as a response, as an output, an answer to its query. So now we start to talk about generative AI. And as we are in a chat mode, we continue to have the output of AI, which becomes the input of your next query, and so on. So it became much more user-friendly. A brief outline for my talk. I will give you some case studies, 1, 2, and 3, and I will try to follow the typical machine learning workflow. My first case study, I will dive into data analysis and then show why is this important to shift towards feature selection, which means selection that are meaningful for machine learning, and then attempt of predictive machine learning. But we shall start with some key concepts regarding data and machine learning. And throughout the case studies, I will also get back to some data concepts. So now we are headed to start. And if I would have one mission for you, for the students, I would really like that you come back home for the weekend and realize you're all doing data-driven work. As scientists, in my opinion, you are in very good position to use AI tools to leverage your research work with AI. As scientists, we know that the data is the way to go. You should believe data. If you don't believe data, you are not ready to AI and machine learning. But if yes, please let's find out it together, and I hope you understand that by the end of the presentation. Because before reaching AI, I want to reframe it, and I will do it many times during the presentation. The bottleneck of any AI application is the data. Everything starts with the data collection, right? I have a few companies coming to me saying, Leo, I really want to implement AI for solve my problem. But they realize that they don't have yet any data flow. They don't have a database related to this problem to be solving. So very often we spend a lot of time, we put a lot of effort in the data collection phase. And you as researchers, you are all used to climb up these steps. You profoundly know your data, right? So you are doing this day after day, cleaning your data, preparing, and of course, analyzing and understanding it. I shall also mention that you can use AI in any of those steps, even sometimes unsupervised learning methods, as I will show at the end of the presentation, to come up with new insights in terms of data results. A brief definition of AI, I think, is needed. I like this broad definition. AI is the ability of machines to perform tasks that normally require intelligence. And machine learning, it's a bit more complex definition, but in general, we could say that if you teach a machine through data to learn a pattern, you can use that learning to then use this knowledge in a different situation. Meaning, the machine learning algorithm learn how to solve a problem. You don't want it to keep it solving the same problem again and again. You want to be generalizable. And then we talk about its generalization ability. Little by little, but machine learning still has trouble with it. We are reaching a extrapolation ability, but this is more hard. This would mean I develop a solution in biology and I want to use the same machine learning model in material science. Then often there are issues, but we might get to this point, I believe, by 2030. We can discuss more about that if you want later. And this is a very visual example. Imagine a kid solving a puzzle. Once it understands the logic behind it, the kid will be boring solving the same puzzle over and over again, right? The kid would like to solve bigger or more complex puzzles. This is more or less how machine learning works. It understands patterns, and then we can replicate it into broader scenarios. Is it clear? Can you hear? Do you have questions so far? Because now I'm gonna enter into more case studies topics.
And there is no question so far in the chat, so go ahead.
All right. So first example will be on exploratory data analysis, and then we're gonna go for feature selection, which is often a result of a well-done exploratory data analysis, I would say. It's important to have in mind that we use a very specific tool for this. It's called SECCM, but we use it mainly because of its high throughput capabilities. What we would like to do was to get big data. And this local tool is connected to a potential stat, and we are able to scan, to probe a surface and get big data, thousands of examples of, for example, polarization curves. But keep in mind, this is all in the local scale. So in local scale, you might expect higher errors and variance as well. In the two particular cases of case studies I will show, we scanned the surface of 316 L stainless steel, and we collect about 1,000 of examples of polarization curves, potential dynamic polarization curves. And this probing was done in random fashion on the surface. Although the technique might allow us to control the location, we have done it without paying attention, let's say, to the locations of the scan. So take home message, think in big data. If you want to use AI, of course, your data in the lab might suffice, but you should in general have more example to comprehend all possible scenarios that your data might dispose. So these are examples of the polarization curves we obtained. I'm almost sure everybody here understands what the pitting is, right? We have a abrupt increase in current density. So in your opinion, what would be a good pitting descriptor out of this curve? How could we describe this curve? For example, this blue one, I would say it has worse pitting behavior than the other ones. And why is that? What would be a good descriptor to summarize, let's say, these different curves? Any idea? Why could I say?
Give the answer, like interaction is not as strong.
All right. Yeah. So we are looking for the EPIT, the pitting potential, okay? And this is our scientific question. I would have liked to use machine learning to estimate, for example, the pitting potential. But before that, we realized that our curves were so much noise that we should dedicate study for that. So let's start with case study 1, published in Corrosion Science, where in fact, we would have liked to quantify, and we actually did that. We quantified the randomness associated with these polarization curves. And from top to bottom, we have different data sets with increased corrosiveness. And I just want you to realize that these histograms, they present increased spread as a function of corrosion aggressiveness. So if you follow these arrows here, they go along with the error. These are just 3D histograms, so this is the frequency of current density that we measure. And I would just like to show you that data gets more and more complex, but we shall better see it in 2D at very low applied anodic potential. We are in the passivity zone, we have normal distribution, but once we amplify the overpotential, we reach the passivity breakdown region. And as a function of corrosion aggressiveness, our distribution of current density goes from unimodal, let's say nearly normal, to a uniform type of distribution with much higher associated randomness, right? So another tip for you, always check your distributions, because from purely machine learning point of view, if you train an algorithm for prediction, it will always be based on the mean value, on the average, and will not, in principle, take into account the spread of the distribution. So when we plot the randomness then as a function of applied overpotential for increasing level of corrosiveness in the tests, we can see how this randomness amplify. And this leads us to question, in fact, the actual definition of a passivity breakdown. So my whole message here is to think probability. We should sometimes question the definitions and try to think of descriptors more as statistical properties rather than point properties as shown in the books. And with that, I think we were more prepared to tackle our machine learning endeavor, which was estimation of pitting descriptors from these polarization curves, from the same polarization curves. And you might ask, why are you showing, right, counting of livestock like that, Leo? I just want to refer to the importance of labeling in machine learning. This is a very well-known example of supervised learning. What is supervised learning? You give your data set labels before applying machine learning. This algorithm was training, and by putting in the data, along with which one of these sheep bodies, this is a sheep, okay? And after that, it's very easy for the algorithm to do a counting of sheeps. We did exactly the same in these polarization curves. It seems complex, but this is one example of polarization curve. We manually label the pitting potential, which is here, okay? So we verify that based on domain knowledge. I assigned out of thousands of curves that these were good estimations, I would say. In fact, we use a linear regression method for that, for getting these labels. And it solved our problem with linear regression, I would say 80% of the time. So what we did, we selected these 80% cases, and we trained a neural network, a machine learning model, to give us the estimations. And of course, if we fit the algorithm with the same type of curve, it gives us a very good estimation because it was trained on these good examples. But there was cases where our initial approach, linear regression one, failed. And by brute force, then our machine learning method was able to provide good estimations in those more challenging local polarization curves. With this, I would like to call your attention to the fact that this is a very complex model, but nowadays it's very light to use such a model. Even offline, you can use it. So we are not, there is no restrictions anymore in terms of scalability of models. In the past, we were very much concerned on model developing side. Nowadays, I would say this is pretty much solved. This type of model can solve pretty much any mathematical relationship. So I think we should put our efforts more on the data side, on the data collection and data preparation side. And once this was done, it was very easy, very convenient to understand the distribution of our pitting descriptors, right? Either the passivity potential or the pitting potential as a function of data set. And this is also important key message. there's a lot of libraries in Python or others for data visualization. I'm a very visual person, but very often I believe for everybody, just plot your data helps to get to know it better and get to know your model better as well. So use and abuse of data visualization tools. And this is particularly important for scientists, right? We want as much as possible to interpret the results, but not only that. Nowadays, one of the main axes of research in AI is interpretability, right? Because AI is still in principle a black box. So the researchers are trying to render this black box as transparent as possible. Why? Because AI hallucination, I would say, is still the major issue in the tech industry. For some very high tech engineering applications, we cannot allow ourselves to deal with AI hallucinations. And unfortunately, even nowadays, state-of-the-art models, for example, the last models of GPT, they still hallucinate 1 to 5% of the time. Of course, if it is just a word that was wrongly used, it's not a problem. But once we start to talk about reliability of electronic systems and so on, these hallucinations become a very big deal. And use of visualization tools, as I mentioned, helped us to better interpret the data. And we realized that our highest data density part out of this polarization curves was coincident with the conditional median, with the median of the population of curves. This explained to us why our mean was shifted, because the mean was very influenced by the high outliers, which were precisely cases where we had stable pitting growth. So we realized that the median could be, in fact, a very good proxy model for us. This is another message for you. Machine learning sometimes is complex, but once you get to know your system, you don't need to use it forever, machine learning. You can come up with what you call simplified models. In this case, the mean was not a very good descriptor of the behavior of the location of pitting potential, for example, but the median, yes, the median was a very good and much simplifier model, right? We can much better understand the median distribution than a machine learning distribution. And we need also to render proof, quantitative proof, and we have done so for those simplified models through residual analysis. Residual analysis is simply the difference between the actual data labels, our ground truth data, minus your estimations. So we compare the estimations of our simplified models, either based on the mean, based on the median, either for passivity descriptor or for pitting descriptor. We compare it against. So the benchmark here are the machine learning estimations, which are the ones that we trust, that we manually labeled and verified. So it's super important always to have your benchmarks. This is also super important for developing LLMs like GPT, Claude, Grok. For those that follow these trends, almost every week we have a new model that is the last super intelligence model. And how do they come to these conclusions? Then they subject the models to benchmark testing. And this is super important, right? Otherwise, we have no clue of the real capabilities of our models. And finally, this is my last case study. I will show how, in fact, we use a unsupervised learning to discover new pitting pathways, new stable pitting pathways. So I already presented you the importance of labeling, of supervised learning. Here, I will also present a bit on unsupervised learning side of modeling. But before that, I need to explain you a bit more the concept behind this study, what was our assumption. Our assumption was that we were tracking down rare events. If we plot the distribution of an entire polarization curve, let's say, we have the head of the distribution, but we are chasing down pits, and pitting is a rare event, either in real life or in accelerated tests like the potential dynamic curves that we obtain. Pitting events are rare, so we call it a tail event. If we model with a normal distribution, we will most likely miss out this information, as you can see. And contrarily, what we would have liked to focus on was on these tail events. So we come up with a function called Mandelbrot-Zip, which is particularly suitable for modeling rare events. We got the inspiration from this book in which Nassim Taleb discusses data, rare events and from rare data in the context of financial crisis, and we adopted it into pitting corrosion. I must say here that this modeling is quite complex, is based on the fractal theory, but the importance is that is indeed able to fit the rarest events, in our case, pitting corrosion events. And I must also say that this work started 1.5 years ago. At that time, GPT-4 was already around, and without the GPT, it would have been much harder for me to implement this idea of research. What would have cost me maybe months or years of implementation, because the code is quite complex, took me a few months, and GPT confirmed at the time this was a good strategy. It was a good analogy we could use to model pitting corrosion events. So another tip, use AI as exploration tool, right? Try to make advantage of it. So this is an example also of unsupervised learning. As I mentioned, this was also important part of this work. And contrary to the algorithm that was counting ships, as I previously showed you, if in that algorithm we need to label the data and say to the algorithm what a ship was, in here the algorithm has no clue what a player is. It's a super intelligent algorithm that in fact detects motion, and without instruction, it was able to detect the body of the players and the location of the players and so on. This is unsupervised learning. So here I show the polarization curves, population of a data set. And just for you to know, this work was done with classic potential stat polarization curves, macro scale. This is a data set of 28 polarization curves. In total here, our big data was around 84 polarization curves. And this is similar to a histogram. We have the frequency here, but the data is ranked. So this is the most frequent value of current density obtained out of the population of curves. This probably corresponds to the passivity range, because here we can follow the data scholar mapped with the potential. And here we have the rarest data points. These are, in fact, after inspection, related to the OCP, because we have a lot of perturbation around the OCP, right? But what we are really chasing down here is the location of EPIT, so the pitting potentials, and they are plotted as red circles there. This is it seems to be a quite smooth surface, but then we apply a supervised learning technique, very well known, and PCA, which is very simple to employ nowadays to reduce the complexity of our data. And then our data is represented differently in this new two-axis space. And using yet simpler clustering algorithms like k-means and so on, we consistently realized that our data could be segmented, and it was segmented into what we call head, neck, core, and tail tip of the distribution. And then we got back to the Mandelbrot space, right? No big surprise, but it would have been difficult for us to try to segment the data portions like that in this space, whereas in the PCA space, these discontinuities were found and these segments were found out. But most important here, when we get back to the original space, so the population of 28 polarization curves, we realized that there were two types of pitting potential points. And most of them were, let's say, I would say a classic case where we have passivity in a lot of the Sunday passivity breakdown, but some of them are these blue lines around there, were a different type of pitting potential population, and they were almost exclusively located on the tails tip, which represents the rarest events of the distribution. So here, as you see, the focus was not at all on developing machine learning models, but on the data understanding. And you have done all of that as scientists already. the fact of using available tools nowadays, data-driven available tools, will just leverage your research. But here's a bit easier to see. So we split the two type of pitting pathways discovered. As I mentioned, this is the classic one, passivity and boom, passivity breakdown. And here on the left, also in red, stable pitching growth occurs after metastable events. So the stable pitching growth is in fact preceded by meta activity. And these blue dots just show the what you call the metastable pitching potential, but the last one. And as corrosionists, I think you can understand that this might be a more critical case of stable pitching growth because they tend to be more active as they already research from ongoing metastable activity. But let's focus on the machine learning parts of the story. So here I just plot the two types of pitting potential points. So in black, this second type of stable pitting pathway, and in white, the classic pathway. Here again, I refrain to the importance of manual labeling based on domain knowledge. Here, I was the one deciding and allocating those labels here, right? And this is super important. Is more important than sometimes relying on algorithms. So this is my ground truth. And case one of pitting pathway, it's pretty much linear relation. And the other one escapes to this pattern and is potentially more dangerous, as you can see. But once we have manual labeling, we can compare, of course, to what our unsupervised approach suggested to us. And the correspondence between those two populations was not perfect. If this was a classifier, it would not have been perfect, but it was quite accurate. So we could finally think of using these two as a machine learning predictive tool and deploy this machine to find in unsupervised fashion potentially the most critical pitting pathways out of polarization curves. And with that, I'd like to, in 1 minute, showcase a bit what we do on my business sides at my company, IAlto. So we have two main axes. We are very much concerned with education and training. So we deliver in local training for companies. We have done it with, especially with medium and small-sized companies. But we also have done a lot of training and courses, mentoring for academia. So we have two clients in Belgium, two Belgian universities. And our second axis of service, we develop custom AI assistants or even machine learning models. So with that, I really would like to thank you for your attention and would be very glad answering your questions and joining the panel later on broader discussions on AI use. Thank you so much.